So, good afternoon. It's a pleasure to have here today Professor David Pritchard. David is a professor of MIT, the Massachusetts Institute of Technology, and he's been there for a long time. And during his life, he was very much interested in atomic physics. In fact, David is one of the founders of this atomic physics with cold atoms, that we have a few representatives here in Brazil, in different places, not only São Carlos. And during his life, he has put to this field all the ideas that actually turn into the field that it is today, including the seminal ideas how to reach Bose condensation. And, well, many people passed to his lab from his collection of students. Many of them got important prizes with their thesis. And 3 of his students got Nobel Prize. So he's one of those guys that he makes Nobel Prizes. And he's been involved in so many things: high precision measurement with ions, high precision spectroscopy with atoms and molecules, atomic interferometry, BEC, of course, Wolfgang Ketterle, Cornell, Andy Hewlett are kind of guys that learn the principles of BEC in their lab. And so he expended his whole life doing a wonderful scientific career together with Dan Kleppner. He's always together with Dan. They share, they start this new field at MIT. And then, now, he said that he considered that his contribution to atomic physics is kind of done. And he started to worry about education. We think that MIT don't have problems of educating people, and that's a mistake. MIT has as much problem as making their students to understand science as we do here. Wait. And therefore, he now starts a new challenge in his life, which is how can we teach science in a better way, in a more attractive way for the student, in a way that students can not only feel pleasure, but feel interested in learning that stuff. And not only that, but he's devising ways to really test if the students are really learning concepts or only learning ways of doing final exams. And he put together a group of people, students, faculties, postdocs, and then he started this new, I would say, part of your career. And his studies is being well seen by all the community, and many places are adopting way of improving, inputting more things in the teaching and testing if the students are really learning. And then we are also worried about this. We want our students to be motivated, to be interested, and we want to make sure we are doing the right way to transfer to the student maximal knowledge in concepts, in everything. So we brought David here, and there is an idea of bringing some other guys along the next semester to discuss, so they can present what they are doing, and we can, I know that we have also many initiatives here in our institute towards this, but it's always nice to speak and to see people that actually gave up the rest of it to concentrate on this and see what can we use and how can we implement things here that are working in other places like MIT, Harvard, and many other institutions in the United States. He started a company. It's called Mastering Physics. And then that's a company that together with, they sell to the students a package, so help them to learn physics. And then he sold the company, And he's said to me that now he's quite busy doing what he's doing, and the things are growing in a way that he cannot even attempt all the meetings that he's invited to. So it would be nice to see what David has to say about those things for us, his experience, why everything we learn around the years now have to be we have to rethink about concepts. After his talk, we're going to have a small discussion, and there is a coffee that will be served. Unfortunately, cannot be here, to a small place, because of the construction. So who is interested in having a coffee has to move to the next building near the door of our director that's here. And then we're going to have a coffee to all the people that attend to the conference. Okay, so David. Oh, I forgot to say that David was my advisor in my PhD thesis as well.
Okay, well, thank you, Vanderlei, and thank you to all the people who are paying for my trip here. I always like to come to good weather. I'd rather come when our weather is bad, but nevertheless. This is a particularly big sacrifice for me to be here today because I really like sailboat racing in my sailboat, and the race is tonight, and I don't think I can get back in time. Okay, so let's talk about this. And you see that the title, I mean, for 40 years I taught in the classroom, I taught people. And many people say, oh, this is great, you're a good teacher, you know, I had high ratings. And now I just really think I didn't do a very good job. And I want to try to have a little conversation with you and try to get you to understand why I think that. And maybe it won't take you 40 years to figure out a better way to teach. All right. So I want to tell you where I started off. We like our students to be able to do complicated problems. So here's an example for those of you who teach. And this is an example, let's see how this thing works. Yeah, okay, fine. So a bullet comes along and it hits this little disc that's pivoted, and you have to realize that angular momentum is conserved about this point, and then the disk starts to rotate, and the question is, how fast does this have to be going so that it will rotate all the way over the top and keep going like that? So you have to use energy for that second part. So the point is this is a multi-concept problem, and there's no single formula in the book that gets you from the initial to the final. So you have to be able to take it apart and solve this problem. So I used to think this was great. If students could do this, they really understood physics. I'll tell you why that's wrong. Okay. So anyway, I won't talk about that. The basic idea that I started off with was that our final exam measures what we want students to learn. And so students had a lot of problems with the homework. And I decided to make an online tutor to help them, and my son did the programming and I wrote the content. And so that's Mastering Physics, and now last year 300,000 people used Mastering Physics, and 2 million people is the company. It was bought by Pearson. If I'd waited a little while to sell it, maybe I could just finance all my research myself now, but I sold it too soon. And 2 million people use this the world over. Okay. So we took the philosophy that the best kind of education is a personal tutor who interacts back and forth with you. And we decided to make an online Socratic tutor. And we had 2 goals that we set for ourselves, that it assess what we really wanted the students to do. If it was a force diagram with vectors, they had to draw the force diagram with vectors, and we had to be able to tell automatically whether it was correct or wrong, or even give them a hint. And the second thing was that it was going to be part of the grade, so that they would complain when it didn't work, so we would make it then work. And the idea was that we could get data and we could use the data to improve the tutoring. So I'll just show you very briefly how it works. We give the student a problem like this, and then there's a question, and this question demands that they put in a symbolic expression with sines and cosines and x and y and so on. And if they have trouble, then down here, they can request some help, and they can get a list of hints, and then they can open the hint that they want to open. This is like a plan for doing the problem. And one of the first things that amazed me was hardly any students received help from just seeing this outline of how to do the problem. Once they saw the outline, they almost always had to go into the hints themselves. I didn't realize how important that was at the time. The students can request these hints, and some of them some of them coach the students with calculations, and some just say, well, use energy conservation after the bullet has hit the little wheel. And then if they submit an answer and it's wrong, even a free response answer like that, over half the time we can be like a tutor and give them a specific response for what they should do. So that's basically how the tutor works, and we have some evidence that it really works. Here's the evidence that we got. We looked at how much I was teaching the students who had failed the fall semester of the introductory semester to mechanics in the spring. So I had a final exam that they took and didn't pass in December, and then a final after our instruction in May, and I started looking at what activities did they do, and how did that correlate with how much better they did on the second final exam. And so look at this. Boy, was I pretty happy. I mean, to go to MIT and get people to grade the written homework and do problems in class and participate in class, that costs $45,000 a year. And to use Mastering Physics, that costs $45 a year. So it's 1,000 times less, and look at how much better it is. Okay. Then we had a way of measuring the students who were copying their homework. You know, it does happen. And so what we found was, wow, you have the students who didn't copy it went up. This is the first pre-test. This is the final. It went up. The students who copied 10 to 30% went there. Students who copied over 50% were there. All in all, so I can answer that two ways. One, they were able to answer the question, all three parts of the question, completely, correctly, in less than a minute. Whereas the average student took 10 minutes, and 90% of them made some mistakes. And these students didn't make any mistakes. So that's the operational definition. And then we did surveys, and we find out, well, they actually did admit in these anonymous surveys that they copied it, mostly from other people, or sometimes they got their passwords and so on. Okay, so that's what I mean by copying. So this is a 2 sigma effect. That's really huge. 2 standard deviations of improvement for using this. Okay. So I'm going to now tell you where I made some assumptions and the evidence that it's wrong. You know, I used to think that homework copying was their problem, and that they would maybe not do so well, but that wasn't my job to stop them from copying. But now I realize this is very important, and we've taken steps to reduce it by a factor of 4. Okay. Then we took a closer look at this, and what we found was that the copying affected those problems that required a symbolic response, but on concept tests, it didn't have any effect. So the students were not. So the long story of it is, on the symbolic it made a 2.4 sigma learning effect, and on the conceptual problems, and even some of those conceptual problems involved using numbers instead of symbols. The same topic, same material, it didn't make any difference at all. So what is going on? How come these things are so different? Because as a physics teacher, what I expect is that when the students have a symbolic problem, that they approach it the way I told you. To do that problem with the bullet and the wheel, I have to think conceptually, and I have to realize that I use angular momentum, conservation, and then and then I've lost some energy, but after the bullet stops and it starts to spin, then I can use energy. So that's how I solve that problem. So how could it be that I could get much better at solving those problems and not be better at conceptual stuff? But that's what this result says. It says there's no connection. Also, I instruct my students that when they have a numerical response, they should solve the problem symbolically and then plug the numbers in, substitute instead of h, put in 3 meters, okay? And so if the students are doing this, there's absolutely no way that you can explain this huge discrepancy. The problems cover the same material, and so this result is unexpected. And I might go further and say, what it basically reveals is that the students are not experts. They're not even little experts. They don't approach the problem the way I do. They do not approach the way that I show them how to solve the problem every time I solve a problem in class. They don't do that, okay? So what are they learning? What are they learning? I think the answer is, we are only teaching them to answer our examination. We are not teaching them physics, or at least the fact that they can answer our examination is only a very small indication that maybe they've learned some physics. And so my lesson number 1 is, just because the students do well on your exams does not mean that they solve the problems the way you think they do, i.e. that you are teaching them to behave like experts at all. Sample bias? Oh no, every student is in that graph. Every student is a point either here that they did not copy, and then you see the difference between the symbolic and the non-symbolic, or up here they did copy, and now you see the differences the other way.
No, I mean the total number of students. This also, because you said you only took the students who did not pass the fall exam.
Oh, sorry. No, on that first study, this study involved the fall course, and it had 500 students.
Yeah, but they didn't pass the fall exam, those students.
No, this is a later class in the fall.
I see.
Okay. So that's why the error bars are so small. I sometimes say to my friends, the p-value, the probability that this happened by chance is 10 to the minus 16. Okay. It didn't happen by. And then once I started reading the literature, and I have to say I'm the way most scientists are, I wouldn't go into the lab without knowing the literature in my field of atomic physics. That would be foolhardy. But not having any training at all in teaching, that empowers me to go into the classroom and change the way I teach according to my good judgment. And that's what I did. And then I started reading the literature, and I found out this stuff is well known, that there's a lot of literature, only since 1980 or so, about the real fundamental differences between the way experts think and the way novices think. And okay, so my second lesson is that assessment and grading is absolutely critical. Especially in a required course, that's what the students are going to learn. What's on the test. Doesn't matter what you say. Okay, so the next thing I'm going to talk about is educational data mining. And I'm going to get behind here. It's not so bad. So here's an example. This data is from edX. That's edX.org is the MIT, Harvard, and now a bunch of other universities online platform to deliver massive open online courses. And so we get 38,000 files on from 27 different computers that make up the cloud, and we put them all together and we get stuff like this. So it's pretty obvious what's happening. The students are learning, right? No, maybe they're not. But everything they do, every click, every time when they're working a problem, then they go to the textbook. I know what problem they're working. I know how far it is from the deadline. I know what page of the textbook they went to. I know how many seconds they spent reading that. I know if they went to another textbook page, then they went back to the problem. I know what they could do at that time or not do at that time. I have all this, that's only like 6 lines in this thing. And I have, if you made a library and you put books all around the edge of this room, I have about 50 times that much information for one course. 100 gigabytes of information, like this. And so the question is how to analyze that to give insight into student behavior. Okay, so I'll show you. I want to ask you a question. The students obviously have lots of assignments, and then the homework in my course is due Tuesday night at 10 o'clock. And what I want to ask you is, Sunday night at midnight, which is long before those students go to bed Sunday night, I'll tell you that too. I know that now, because I can see that in all the clicks. What fraction of the homework do you think that's due Tuesday night at 10 o'clock, do you think they have done Sunday night at midnight? How many people think that it's under 10%, less than 10%? Okay, yeah, most people, right? How many people think it's over 1/3? They've already, 2 days before it's due, they've already done 1/3 of the homework in advance. This is a required course. Okay, well, okay, I mean about 2 people. Usually, yeah, that's about right. Usually about 1% of the audience thinks that. Well, here are the data, okay? And this is the majority of the students copy less than 10%. And here they are, Sunday night, they've done half of all the problems. They've finished half of their assignment. These guys are going to copy 20 to 30%, but nevertheless, Sunday night, they've finished 1/3 of their assignment. Okay, it's hard to believe, you know, we couldn't predict that. Now I'm going to show you some other data here. This is how many pages in the e-text were viewed day by day. This is a traditional fall course from August through December. Okay, you see that curve? Tells how many accesses there were to the textbook. Okay, I'm going to ask you a question you have no way to know the answer to. How many examinations were there in this course? Okay, so basically what happened is they started off, and every week they read the textbook, and that decayed, and after the first exam they realized that wasn't the way they should spend their time, and they basically flatlined except for the exams. Okay, so I showed this to a friend of mine who spent 6 years writing a good textbook, and he said, damn it, I should have just written a short handbook. Why did I bother writing a textbook when all they're going to do is review this before, the night before the test, or the 2 days before the test. These things are 2 days wide. Okay, next question. This is in EE, but it's a science course. In this course, they could, when they did the homework, this graph shows you how much time they spent on the different resources in the course, and it shows you which ones they used the most often while they were doing their problems. And so here you see they overwhelmingly used the discussions. And then the most time, and then they went to the labs. It was a course with an active simulation lab for electrical engineering. And then they spent the most time in the lecture videos. And when I showed this to my friend about the book, who wrote the book, he said, well, maybe I shouldn't have written the book at all. Okay, but then what is their strategy when they're doing examinations, the midterm and the final exam? Well, the thing that they go to most now is old homework. That makes sense, right? Because on the homework, there's no old homework is not relevant. You're doing something new. But on the exam, you go and you find the old homework. That's the first thing they went to. And look where they spent the most time, on the book. Okay? So what I really want you to do is to take home from this, these 3 examples that I've shown, my second lesson, my third lesson actually, which is that we really don't know very well what students actually do. We don't know how they spend their time. We don't know when they solve the problems. We don't know how they use the book. We don't realize that there's a big difference in the strategy between the working homework problems and working exam problems. We didn't know that. I've been teaching these guys for almost 50 years, and I didn't really know those things. And so I wonder, when we give them advice about how to study and how to learn this stuff, what authority do we have? We have the authority of someone who doesn't know anything about what they're already doing, and certainly doesn't know what will help the most. So that's what I'd like to find out as we go through, and we try to do data mining. We try to find out what resources or what order or what habits actually help students learn more. That's what I'd like to do. And that's why I gave away my spectrometer, and I gave away my lasers, and gave away my atom interferometer, and ultimately stopped collaborating with Wolfgang. Okay. Now, I'd like to address a subject that I once brought up in a faculty meeting in our department, and we have a person who's the associate head for education in our department, and I said, well, maybe we should, before we debate whether we ought to put the rocket, it was a discussion about the rocket problem in mechanics. Before we do this, maybe we should try to figure out what we really want the students to take out of this course. And the associate head of the department for education said, no, we all agree on that. Let's just discuss the issue at hand. Okay, but we don't agree on that. We haven't even thought about that, really. Most of us haven't thought about that. So what should we be teaching? So what it turns out is we teach them our conception of physics. Should we be preparing them for their lives? Should we account for the fact that 95% of the students in our introductory physics course are not going to be physics majors? They are going into engineering, or they're going into biology, or at MIT they have to take our course even if they're going into economics or architecture or music or whatever. They have to take our course. So maybe we should teach them learning habits that are useful in any course they take. But of course we don't know what unit learning habits are useful in physics, and we don't know if the same ones are useful in math. So we're not in a very good position to give any advice. But nevertheless, I thought teachers were experts about this, and so I did a survey. And here's my question. The academic calendar changes, so you have 20% more time at the end of your course than you used to have, and you have the same number of topics to cover. So what are you going to do with your extra time? How are you going to spend it? And so here's what the instructors, so I asked a lot of people, and I condensed this into 4 categories of things and 12 different items. Maybe there are only 10. Yeah, there are only 10 here. 2 of them didn't get many votes, so these are the 10. Okay, so now you look at the instructors, and the number one thing the instructors want is to teach their students not to just accept the answer that they have just calculated, but to think about whether it makes sense. So I often tell my students, look, well, you went to MIT, and so you're going to be the boss. And then some Friday, an employee is going to come to you, and you're working in an engineering company. Employee says, okay, boss, I've been working on my computer program for 2 weeks, and I've calculated that the cables in this bridge we're building have to be 0.7 meters in diameter, okay? And how are you going to tell? I mean, it's important that that answer be right, okay? Very important, because if it's too small and the bridge falls down, it's not good for your firm. And if you make the cables too big, you spent too much money making cables too big that you didn't have to, and you're going to lose money on the job, okay? And it's just for professional pride reasons. It's nice to get answers to questions really right. You know, when you do research, when you do the real world, you don't have that many questions, and it's going to take you longer than 15 minutes apiece to answer them, but you'd better get them right. So how do you check that over? So you have to have some conversation with this person, not with their computer program, and you have to say, well, wait a minute, I know this Verrazano bridge, it's about the same size, but the cables there were 1.1 meter in diameter. And how come for the same kind of bridge, you're telling me that it's 0.7? Come on, the bridge is going to fall down. And then that person that you're supervising has to say, well, you know, we're using much better concrete in the roadbed. It doesn't weigh so much. So we save about 15% there. And then the steel that we're using in the cables is twice the tensile strength of the one that they used back in 1972 when they built that bridge. So that means we can shrink by another square root of 2. And so if we started with 1.1, we'd get to about 0.68, 0.7, and that's what I've got. So it sounds reasonable, okay? So that's what I mean by making sense of the answer. That's what the professors want the students to know, because it is very important. Also, we don't want to teach wider content. That's the last thing I'm going to do with the time, because I know we have so many topics in the curriculum that we have to go over it too quickly. And the students don't really learn it solidly. They just learn how to use the formulas, but they don't really learn understanding. So this is what the teachers think. And then I got some friends, and we, oh yeah, the other thing we don't like very well is to teach them the relation to everyday life, because we want people to understand that physics is abstract, that just a few principles govern the whole world. That's what we really want to teach them. That's what we believe in our hearts. So then I got people to ask a total of about 400 students. And now here's the students are in purple. So right here in the middle, there's a lot of similar opinions. I'm going to blot that out. Okay. Now what do you see? The students want to know wider content. They've already studied mechanics, Newtonian mechanics. Why? That was before the country, before we had any country here, 1600. I mean, I want to learn about quantum mechanics. I want to learn about relativity. I want to learn about the inflation of the universe. I want to learn about great things, and you want to teach me about what Isaac Newton said? Okay, that's one problem. Now another problem here. You don't want to teach. I want to learn about why this stuff is relevant to my life. Why should I spend all this time studying physics? And so when you look at the correlation coefficient between what we want to teach and what the students want to learn, it's minus 0.4. And what that means is that we want them to go lead them in that direction. And it's not as if they just wanted to go in an orthogonal direction. They want to go 120 degrees different direction. They want to go back there, and we want them to go there. And we expect them to march joyfully behind us into this. Come on. Okay, so we're like having a conversation, and we're saying, you'll read the college catalog. You're going to be a problem solver all your life, and we're going to teach you starting right now to be an expert professional in problem solver. And the kids say, look, the catalog, it's just like the Bible, and I'm going to quote my part of the catalog, and that says that freshman year is for exploration, and I don't have to pick a major until my sophomore year. And so please tell me, since I'm looking for a major, why I should spend 10 years learning physics. And we don't talk to them about that, and they don't talk to us about, I want to become an expert yet. They haven't even decided they want to learn physics. So anyway, I just want to summarize now. I think we should pay a little more attention, and I think Vanderlei is actually in the sort of lead of this, of trying to figure out why physics is relevant to their current or their future life. Why they're going to learn important learning habits, why the stuff why Newtonian mechanics, why Newton was the greatest scientist who ever lived, okay, and why it caused the Industrial Revolution and means we're still not living in mud huts. Well, that's a little short, but we're living as well as we do because science has enabled, engineering has enabled the world we live in. Okay, so now here's some bad assumptions that I confess to making. That's what I used to believe. I don't believe that anymore. Students learn when you tell them something is important, like checking over the answer. They will learn to do it. Not unless it's on the examination. And even if it's on the examination, they may figure out some shortcut way to learn to solve the problems like that. So they aren't really learning what you think you're teaching them. And then we have a reasonable idea what these students are doing to learn. I used to think we did. I used to think I did. Now I know I don't. And then we think our final exams are representative of the things we want our students to learn. But in fact, they didn't learn to do those problems the way we thought they did. They learned some shortcut way that doesn't have anything to do, or has very little to do, with genuine expertise in physics. And I thought homework problem was their copy, and then I thought that the students knew that they needed to teach the skills that we are teaching them, and they don't. My students don't even think that if I ask my students, is Newtonian mechanics going to be important to the subject that you major in, about 90% of them will say no. At MIT, they're going to be mechanical engineers, civil engineers, aeronautical engineers. Whatever they do, they're going to have to know about mechanics, but they don't realize that. Okay. So we start, and then we sometimes believe we start them to becoming experts, and that's totally untrue. And maybe one consequence of this is these data here, that in the United States, the physics enrollment has gone like this for over 50 years. No, that's, well, it's sort of 45 years. It's just been flat, 6,000, maybe 7,000, 4,000, but fluctuated in between. And all the rest of STEM has gone up by a factor of 3. When I was a student, a fifth of my class at Caltech were physics majors. Oh, STEM means science, technology, engineering, and math. It's a very common phrase in American education. Okay, I won't read you what Sheila said about this. So, okay, now I want to tell you what we're going to do. And I want it to get to success in teaching, and I want to quote Winston Churchill because he had a lot of wisdom. And you see the relevance of that, right? Success is the ability to go from one failure to another with no loss of enthusiasm. Okay? And so I'm enthusiastic about what we're going to do, but I don't have any evidence right that it's really going to work already. It's going to be just as bad as what we did for the last 40 years, and that's Winston Churchill. So I want to tell you, let's see where I am now. Okay. Right on schedule. Okay. So about a pedagogy that we've developed at MIT, in my education groups, a lot of those people whose picture you saw before, where we are trying to teach them a new way to approach problem solving that will give some indication of there being more, and then see if we can actually measure what we're doing. So I want them to think like an expert, to organize their knowledge, to arrange the core knowledge into models. When you really look at it, we don't, in physics, we don't go back to Schrodinger's equation all the time. We think in terms of the two-level, the interaction of radiation with the two-level system. And we know of that, several different ways to describe that little phenomenon. We use the little models. That's the way working scientists work. That's the way engineers work. They know the shape, the catenary shape of the bridge. They know how to derive that. That's a model for a suspension bridge. And then when they make a cable stay bridge where they don't have one big cable, but they also have these other little cables, they have to learn a new method because it's not the same. Okay, so that's a different model. And we have to get them to realize that F equals ma is not the same as 3 equals 2 plus 1. 3 equals 2 plus 1 is mathematical truth. And F equals ma is a relationship between the interactions, the forces, and the motion that applies only for a single particle under non-relativistic conditions, non-quantum conditions. There's a whole host of assumptions that go into this model of being able to apply before you can apply F equals ma. And the students don't realize that. They treat F equals ma the same way they treat 3 equals 2 plus 1. And then to solve the problems, the point is to solve the problem, to be able to make a plan for the solution, to check if the answer is reasonable. Okay, I was going to say something, but I think I better not. Okay? And then I'd like them to learn that physics is really elegant, that just a few laws will explain a huge range of phenomena. It's really, F equals ma was an equation of everything when Newton wrote it down. It explained things like what happens when galaxies collide even, although those people didn't know there were galaxies. You know, it explains how bacteria move around in a fluid, how the viscous forces are really dominant, and how they have to make little propellers to get around that, because if it's viscous, just moving something back and forth, slow this way and fast that way, doesn't work. Explains all that stuff. They didn't know about bacteria either. Really, it was an equation of everything, if you knew how to apply it. And I'd like them to understand that beauty. So here I'll show you, and I don't have time to really show this in significant detail, but we basically try to teach them that there are 5 major models in mechanics, and that the models, yes, they have equations that indicate how things change. In fact, it's always the same thing that changes the same thing. And Newtonian mechanics is about how forces or interactions change the motion. And then you might measure the motion with the velocity or the momentum or whatever, and that depends on whether you have a single particle, then you can use F equals ma, or whether you have a multi-particle system, and then you have to use momentum laws. And so each one of these has its own specific conditions, the kind of system that it applies to, the kind of interactions that are important, just the net torque or the external torque. And once you get this core model in your head to organize all your knowledge, then you can go and approach problems saying, in this problem, what is the system? What are the interactions that are important? What model of these things suggest? And so that's what we're trying to do. In short, I sometimes say, we're trying to write chapter 13 in the book. So chapter 1 is about acceleration and velocity, chapter 2 is about Newton's laws, chapter 3 is about applying them, and momentum, energy, angular momentum, rigid body motion, but there's no chapter that says, okay, you have a new problem, which of these chapters you had before actually do you use to solve that problem? How do you go about recognizing that? We assume that the students are little experts and that they can recognize this all by themselves. And it's not true. They resort to some method of solving the problem, like look at the unknowns, look at the symbols that are given in the problem, look at the unknown, look down the formula sheet, try to find a formula that's got those symbols in it, and then solve it for, I had a student once at MIT, I was helping a student, and the student had to find the tension in a string. And he did it almost, he didn't quite finish the problem, using the perfect gas law in which there's a capital T, just like in the problem, but it means the temperature, okay? It has nothing at all to do with motion or pulling, the work you do. And so I remember sitting there watching this guy, and then he had P, and he said, oh, P is mv, that's momentum, and the mass is given and the velocity is given. And V, oh, there's another velocity given in a problem, that's the V, and he solved all except for one symbol, and he turned to me and he said, how do I get N? And that to him was the key question in solving this problem, using the perfect gas law to solve about the motion of a block, okay? And I said to myself, if this student passes, I have failed. Okay. And that student failed. And so I felt okay. I felt better. I felt bad for not having taught him anything, but at least I felt good because the fact that he obviously didn't know anything, he wasn't able to pass the course. But what I should have asked was, say that in that problem, instead of labeling that arrow on the block as T, what if I'd labeled it F? Then there's only 4 equations with F, and he would have figured out which one was, and he would have gotten 9 out of 10 on that problem, or 10 out of 10, because he might have mixed up V1 and V2, because he didn't understand the initial and final of that concept. But he could have gotten 9 out of 10 with this method. And I didn't ask myself, what if I had labeled that F? So, okay. All right, so the conclusion is, we have to be like the way you've always trained experts with the apprentice system, or what the education people call cognitive apprenticeship. But basically, it involves the students. It involves me doing the work, showing how to solve the problem, and then saying to the student, okay, so now you stitch up the bottom, you stitch up this thing and put the sole on the boot, on the leather, and stitch it all together. And then I look at that and I say, wait a minute, you're not pulling the string tight enough and it's going to leak. First time that guy goes out in the rain, it's going to leak. So I have to give feedback to teach novices how to be experts. That's the point. I'm an expert, I know what's important, and I have to teach the students that. So we had to flip the classroom. And so we had to coach. And so then we decided to write some online material to get the students ready. Then it also actually can mine that data, hopefully in real time, but not yet, to inform us what are the difficulties the students are having. And so anyway, we made a complete e-text. But I want to show you, and then 80% in our class, 80% of the time is students working the problems in small groups, and the TAs and myself walking around and talking to those students and answering their questions. And as the people who had lunch with me today know, if they don't ask questions, I ask them back, I say. And then I tell my TAs, the most important lesson is this. Let's say the student writes an equation on the board and it's correct. And they say to you, oh, professor, is this right? Do you know what my instruction to the TAs is? Never say yes. Never say yes. What you should say is, where did you get that equation? What physical principle underlies that equation? Do you have confidence in that equation? Where did you get that, the idea to use that? And that's what you should be discussing, because that's what experts can do. They can sort through the information, figure out what's important, and then go through the physical principles and write down the equation. It's not important if the equation is right or not, whether they got the answer right or not. It's important whether they know the process of solution. Okay. So anyway, here's an example, and it's a great example, and I'm a little behind, so I'm going to skip through it. But you can see that the students they've drawn a picture, they're following system interaction model, they're writing all that down, and then at the end I can ask them, at this stage I can say, do you know how to solve that problem? What are you going to learn from all the algebra? And they're going to say, we know how to solve the problem. And when they came in, they could only say that after they'd done the algebra. So that's what we're really trying to teach them, how to plan it and know whether it's going to work. So, okay, so what's some evidence that it works? I'll skip through that. So the first thing is the MIT final. We started this off as a little 3-week course for the students who received a failing grade in the fall, or at least got a D, not an F, but a D, so they couldn't go on in physics. And so that's how they came in. And 3 weeks later, they'd gained 1.2 standard deviations, and they scored average on another MIT final. But there's another thing, too. Carl Wyman's group at Colorado, building on two of my heroes, David Hestenes and Joe Reddish, building on their work, made a class, okay, see that class? What it stands for is Colorado Learning Attitudes Towards Science Survey. And it measures the expertise of students' attitudes towards learning science. Whether they think that physics is a big pile of formulas, which is a novice view, or whether they think there's actually just a few principles and a few core models, and that's what physics really is. Or we might ask them, if you can't solve the problem in the first 3 minutes, are you likely to be able to solve it? Well, an expert isn't really going, for 3 minutes. Well, hell, sometimes I spend, 30 minutes on a problem trying to figure it out. But a novice doesn't have that approach. A novice only can look down the formulas. He couldn't find ones that fit. 3 minutes is up. They don't know what to do. So that's a novice approach. So one of the things that came out of the research on this by all those people that I mentioned is that the average physics course, the introductory physics course, reduces the expertise of students as far as learning science is concerned. And this gray band is what you typically get. Well, we do better than that at MIT. We have these red points. And as you can see, in every case, the red point is either in or above the standard course. Okay, so that's because we work hard at MIT on education, and we learn to educate just the way our parents, our scientific parents did. And I know it's a great lecture when I hear one, and I therefore know it's a great lecture when I give one. And the fact that 99% of the people in the class do not think the way that I do, or even that I did when I was a freshman, I don't care about that, okay? So, but anyway, we work so hard at it, maybe we do a little bit better, or maybe we just select better people. Now, in our course, after 3 weeks, here's what happens. All these green points, and this one here is about their confidence in solving problems. So, I mean, we didn't set off to improve their attitudes towards learning. It was just a result of what we did. Another good thing to look at is how did the students do when they go ahead after our mechanics course. Then the 3-week course, they can put them back in with their other students in the fall course in electricity and magnetism. And we look at how they did. Well, the year before we started teaching, first of all, this is their grade the student's grade in mechanics, and this is the student's grade in E&M. And just look at the top part of this curve here. You can see there is a very good correlation. The coefficient is 0.7, which means it only explains half of the variance, but it explains half of the variance very nicely. This is the students who took our course, before they took our course in this range the year before, and they didn't even perform, well, probably not quite up to expectation. And these are the students who took our 3-week course, and they're performing a couple of, like 3 standard deviations above what you would expect, and 3 combined standard deviations above this. Okay, so we're really making a difference, at least p-value is only 2 parts in 1,000, but I think it's quite probable. Now, I have to say, these students here were students who got an F. Oh, these are worse students, and we didn't do so well for them. We didn't get them up to par. We didn't improve them much. And that's what we're working on in the spring, but I won't go into that. These are students who took a whole nother semester because they got an F. They failed 801. They failed fall physics. They had to take a whole nother semester of mechanics, the way we usually teach it, not from me. And then they went into E&M. And of course, the second time they took it, they had to get a grade up in here in order to pass. But we don't, to predict their grade in 801, we go back to the F they got in the first place. And we see they're right on this curve. So they learned how to solve the problems on the final exam, but they did not learn any skills about problem solving or any confidence that they could transfer ahead to the electricity and magnetism course. So that's what we're trying, those are some of the issues we're trying to address. Okay, so recently I heard a talk from Carl Wyman. Oh, no, I have actually caught up. So I'll just show this. This is the same data, examination by examination, for the people who took our review, for the control group the year before, and for the second review group who didn't pass, but nevertheless they did a little better. But the point is that this kick we're giving them to do better in E&M, it isn't just an initial kick on the first exam. This continues all the way through to the final. So I don't really know what we did. We didn't teach them any E&M, but somehow after taking this course, they're more expert or more self-confident, and they can do better in electricity and magnetism. Okay, so I'm not bragging this course. We can't scale it up because it's very intensive with lots of TAs going around and talking to the students. And so we have to start thinking about ways to do this more efficiently, more cost efficiently, because we cannot keep education growing in cost as much as it's grown in cost in my lifetime. At the rate it's growing now, it's faster than inflation. It's faster even than medical expenses. Medical expenses is about 4% above inflation, and education is about 6% above inflation. We cannot continue this. We've got to figure out a way to automate this, and that's why I've switched to online education. Okay, so I saw a talk by Carl, and he talked about what are some components of expertise. That's what we're trying to teach now, I think. You know, in this age, there's no point in teaching them facts. You know, you just, if you want to find the capital of Alabama, the state Alabama, or the province of San Paulo, you just hit San Paulo capital return, right? And bingo, up comes the information, and it even tells you something about that city that's the capital right away. You want to remember that stuff. All you have to do is remember how to use a search engine. Okay. But what is the separation between you and the computer is that somehow you're supposed to be an expert. And so what can experts do that the computer can't do, at least can't do yet? Okay. So first of all, experts think in terms of concepts and mental model, and they understand the selection process for what mental models to use. This is Carl Wyman's words. These are, and then they're good at recognizing what's important and what's not important. I mean, we give, I have one study that shows that in a textbook, about 96% in a standard textbook and 92% of all problems in a reformed textbook have just, in the problem statement, there's just the necessary and sufficient information to solve the problem, and it's obvious that the professor intended a certain method to be used, and there's one and only one correct answer. How many real-life problems come that way, with just the necessary information and not a lot of superfluous information, or with all of the necessary information that you need, or they only have one way to solve them, and it's obvious as soon as you look at the limited set of information that's given. Well, that doesn't happen in the world. Not in the world I live in. It's always much more complicated than that. So how, in doing these little toy problems, do we expect them to be prepared for life and be able to do something that the computer can't do? So they're good at figuring out what information is needed to solve the problem, and they're good at checking over the answer and seeing if the answer makes sense, if the conclusion is right. And they're good at testing models and developing models, because sometimes that's what research is about, is developing new models. And lots of times in a concept, like, let's take a very simple concept, which is motion with constant acceleration, and I could demonstrate this just by dropping it. And now, but it's not mine, so I'm not going to. So let's imagine I have a strobe picture. I go click, 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 pieces on the ground. Okay. Well, that is a representation. That strobe picture is a representation of motion with constant acceleration. Or I could say, oh, the formula is S equals minus 1/2 gt squared. That's using algebra, but it represents that motion in the case that I dropped it without throwing it up or down. Just, okay. And these are different representations of the same concept. And if students are going to understand that concept, they have to understand how to work with these different pictures, how to figure out from the strobe picture what the acceleration is, and how to interrelate that to the equation, and how to look at a graph and say, oh, that's motion with constant acceleration, or it's not. Okay? And all too often, to get through the syllabus, we just teach them the most convenient representation, often is just algebraic, and then we expect them to know all the rest. But that's not, experts have to be able to interrelate these things. They have to practice doing that. Okay, so anyway, so now how does MAPS measure up by this standard? Well, modeling, we're pretty good at that. Okay, we are very specific about what is the important interactions, what are the agents of change. We know they need to know about the system and they need to know about the interactions. Well, we don't really help them. I mean, I usually throw in a couple questions about this on the test, but we're not really very good at teaching them what teachers most importantly want to teach the students. Remember that graph? To make sense of the answer was the #1 priority of the teachers to teach. And I have to admit, I don't do that very well now. And so on, okay? Now, in Carl's talk, he went on and he put down those things and he said, now let's look at our problems. And basically he said, look, they all provide the necessary information. They tell you what to neglect. Neglect air resistance, it says in the problem. So it doesn't, those expert characteristics you don't need. They don't ask for why it's reasonable, so they don't have to know the answer to the question that I tell the TAs to say, where did you get this formula? Usually there's only one thing, and it's usually possible to solve the exam problem quickly and easily using a particular method. So basically, none of the characteristics of expert thinking are required to do the problems that we base our whole grade on. And this is a rather stunning realization, how far off base we are if our objective is to teach students to actually become more expert. Okay, and then in all of this, there's the role of the teacher, but I had better skip over that. Okay, basically it's to be a cognitive approach, and you can look at that. But I want to talk, I know lots of people are interested in MOOCs, and so I want to say, can we use MOOCs to help teach students better, or at least more cheaply? And so, you know, I have a whole, I just want to skip over this very quickly, but 2012 was proclaimed to be the year of the MOOC. At that point, there was not one single paper published that showed that there was any learning in the MOOCs. All the papers were about how 3 million people had signed up at Coursera. Of course, less than 100,000 had actually finished the damn course. But the news was that 3 million people signed up, and that all the good universities were doing this, and everybody had better follow suit. So actually, I'm going to present, I'm not going to present, but we have evidence that the conceptual gains exceed that in a traditional classroom in our MOOC. And in case you're interested, take down edx.org and go to that website and look under MIT courses, and you will see our course. It just started 3 days ago, and the first assignment is June 22nd. And so we have, I think, 9,000 people signed up, and I expect to get about 1,000 to finish, maybe more like 700. Okay, but now I want to ask you, is there a simple way to measure learning? We talk about learning. How do we actually measure it? We can't improve it unless we have a measurement. And so one standard way of doing this is very simple. You just give them a test at the beginning, and then you give them that test at the end. And it turns out there's a lot of evidence that they don't remember the questions from the first test and the second test. It's not like me. When I got a question and I couldn't answer on a midterm, boy, if I were given that question on the final exam, I could do it. It was a gift. Okay, and maybe that's true for a lot of you, but you're all academics, right? And maybe you probably wanted to learn this stuff. All right, anyway. So this is the basic way to do that, is you make a plot of what score they got on the beginning test, the pre-test, and then you look at how much gain they had. And if you think about it, say they got 80% on the pre-test, the most they could get on the final is 100%, so they could get just this much gain. But if they only got 10% on the pre-test, boy, they could learn 90% of the material before the end, right? So, and then of course, so then you define this thing called the normalized gain, which is basically how much gain they actually had divided by how much they would have had they gotten the 100% of the final. They learned everything. And so typically, you're going to find something like a normalized gain of 0.4. Okay. So in our course, so G is basically the fraction of what you didn't know in the beginning that you did know at the end. Okay, that's a simple way to interpret it. So in our course, in 8 MREV, this is the result. G is 0.3. And what's important is we had so many students, we could look here at, 4 here. This group were the students who did not have calculus in college. So they didn't do very well coming in. They were the lowest group on the pretest, but they learned as much as anybody else. They had the same normalized gain. And then this group here is number 1, and this is the physics teachers, and so on. I mean, there's the average sort of non-physics teacher in the course. But the point is that, and then we see the same thing here. I want to show you one of the pieces of education research by a guy named Hake. And he looked at 6,000 students in 62 courses in high school, in college, at great universities. This is Harvard right here. These are these curves, and what you see is 2 things. The colored symbols are in a traditional course, And the open symbols are in a course that, oh, whoops, sorry. Okay. I just wanted to make the point that if you look at the point 3, which is what we got, all of the traditional courses that were studied by Mr. Hake, they were all less than that. So our MOOC is doing on conceptual learning as well as traditional courses. Okay, it's better than traditional courses. Now, these are the traditional courses down here. These are the interactive engagement courses up here. The point I want to make is that when you move from lecture-based courses to research-developed courses, there is room for a huge improvement in how well we can teach students, in this case, conceptual knowledge. Okay, so I think, in view of the hour, I better skip through this. I think MOOCs are off the track in a lot of regards, but I think they're good because they offer us the chance to really start figuring out how online education can be done. And there's different ways, but I think most important, they force us to ask, what are the students really getting for their tuition that they can't get for free on the internet? And I think as teachers and university officials, we'd better be able to answer that question in the next few years. And I want to show you just 2 more transparencies for what my vision and what I'm working on as far as the future of college education. So I really think we'd better start measuring learning, and we have to use research. We ideally want every teacher to use resources that have been proven by research to work. Okay, that's pretty hard to be proven to work or has good evidence that they work. Secondly, we want to make it easy for the teacher, like mastering physics. Why do 2 million people use mastering physics? Because they look in the library, they see these problems, they can trust that those problems are good, they have information about how difficult they are, how long it will take their students to do them. They make little clicks and then they're automatically assigned to their students, and it's automatically graded, and the students get help, so they don't even come to office hours anymore as much, and the teachers don't have to spend a lot of time grading. Okay? And then we have to have real-time assessment. So I think of trying to do this. I have about 5 people in my group right now and a couple of undergraduates. They're people too. And so really, this education stuff, mostly we think of it as involving students and teachers, but it has to involve education researchers and developers, okay? So now, what's the objective? The objective is to get a library that's calibrated, that is vetted, that is reliable, and that has all different kinds of research-proven resources for problem solving, for being able to recognize what's important in a problem, for conceptual learning, for all different aspects of expertise. We need research-proven resources that can teach this and that can measure it, and the measuring shows that the teaching ones work. Okay, that's the golden age. So our way of doing this is to have a lot of students come to our MOOC and then take the results, we put these problems we're developing into the MOOC and then use data mining and psychometrics to see how well they work, and then to recycle this problem. Now, we also have a MOOC for teachers, or we have a section of this for teachers where they learn pedagogy. They can discuss how to teach this stuff. And also, we hope to get them to suggest new kinds of resources, and then we'll put them through this system. And ultimately, we'll have this library, and we're working on a course builder interface where the teacher can assign the resources that they want, that they can trust, to their students, and get a report on how their students are doing, and it can get graded automatically. And so, to me, this is the promised land. And so I want to stop there. Thank you very much.
So we have time for a few questions and comments and suggestions. And Holland has few of each.
You mentioned mechanics and E&M, right? And both are sort of similar. You have equations, you solve, and so on. I find teaching thermodynamics, it's much more difficult. Have you tried?
No. Yes, I have taught it in the past. I actually started the undergraduate course in Stat Mech and Thermo. And I realize a lot of what you mean. And I've had students who left my course and took it. I was sitting in the dean's office waiting for some discussion with the dean a couple of months back. And one of my old students from like 2 years ago rushed in and he said, Professor Pritchard, I want to thank you for the SIM method, because I started thinking in terms of the system, and I realized how incredibly important it is in thermodynamics to specify your system. So but yeah, there's a lot of other problems, and a lot of it is our sloppy words. We talk about heat as if it were a substance, but it's really a process. It's really an interaction, okay? And we talk about heat as if it were phlogiston, which is what people thought in the early 19th century. And we can't confuse the students. I mean, I remember a comment in Eric Mazur's class, and it went like this. He said, okay, so we're dealing with this collision here. We're using momentum, and then you tell us that momentum is always conserved, and that's why it's important. And then you tell us, but for the car, it's not conserved, and for the truck, it's not conserved. But then, if you consider the two as a system together, it is conserved. Is there any reason to not understand why I am completely confused? Right? Because we were using conserved to mean constant in this system, and we weren't careful with the words. And the student couldn't figure out what we were saying. So that's an important thing. Maybe there's another question. I mean, basically, you have to do research about every single subject and find out what are the real problems. In mechanics, the students can't tell acceleration from velocity. And you have to really be sure they can do that, or you can't teach them F equals ma, and to really understand F equals ma until they really understand what acceleration is. Okay, next.
Professor, eu queria saber qual a carga horária dos cursos. Alguém, por favor, traduz. What?
Yeah. He wants to know what is the time that students are expending today with the teacher, with their activity. Can you give us an idea?
How much time?
Yeah. What is the
Okay.
loading, time loading?
Yes. Okay. No, it turns out that there's a lot of evidence that, at least in the United States, the average amount of time that students spend outside of class has declined from something like 18 or 20 hours to maybe 14 or 15 over the last 30 years. That's not true at MIT. I know how hard we make the students work. And in the classroom, so we have, for our typical courses, we have 5 hours in the classroom. So in my course, there's two 2-hour blocks, and then there's a 1 hour of a little discussion and a quiz every week. We have what's called a flipped classroom. So there's only recitation. And 80% of the time, the students are working problems. And then 10% of the time, I'm saying, wait a minute, guys. Look, I see lots of people making the following mistake here. And then I elaborate on that and what's wrong about it, or what's right. It's got the right idea, but it's wrong because of this. And then they go back to working the problem.
Can you explain a little more about how the MOOCs is used? Because it's massive open online classes, and
How the book is used.
The MOOCs, the MOOC system.
Okay. I see. So
How this operates in the.
Okay. So, all right. First of all, MOOC, by its name, means that this is a freestanding course that anybody can take, and that it's self-contained. You don't need a book. You just need what's in the MOOC. And the MOOC might have lecture videos. It might have a textbook. it might have notes, it has discussion forums, it has problems, it has quizzes, the whole thing. Which is why I really love it for research, because I can now find out. I mean, in my on-campus course, I do not know if Vanderlei, my student, I don't know if he even bought the book, let alone whether he used it at all. And now I can tell which page he used when and how long he read it. So I really have some data, okay? So the MOOC as a freestanding entity, I think is in many ways terrible. Because what they're doing is putting online the lecture method, which all the research shows doesn't work very well. Why don't we go back to a personal tutor, much like Mastering Physics, where we try to emulate an individual personal tutor who can respond to your particular wrong mistakes? Why do we do this? Oh, I'm the big professor, I'm really great because I come from MIT and I can teach you all about this. I can explain it really clearly, which is true to me, and then you will understand it to you, which is just not true. Okay.
Just one detail. Do you know the Moodle system? You know the system?
Yes, the Moodle system.
Moodle system. A Moodle with a wiki isn't basically the same thing.
Okay. So really, it's not the same. Okay, so what's happened in the public mind is that the fact that Harvard and MIT started with the MOOCs has made everybody start to consider what's really good about online education. And so Moodle is an example of a system that's been around for a long time, which is really I call it a course management system. It's really to post announcements, to distribute PDF files to your students, to have little multiple choice quizzes. It doesn't do it for me, because you should have symbolic things. You should have, there are discussion forums in Moodle too. So Moodle has a lot going for it as a supplement to the classroom. The idea is, why should the student come in and listen to me lecture when they can see that on the internet? You know, they can, and the advantage on the internet is that when I say something that's crazy or that they don't understand, they can stop, they can rewind, they can play it again. There is evidence that you do better learning from a lecture that you can reverse and play again than you do from the real lecture. There's no real, in a lecture, no real communication between us. I don't know what you're thinking. So I think that things like Mastering Physics, if people who did them, like me, had really understood about education, it could be a lot better. But it would not have sold as well.
I was looking at some of the things that you thought that it was important that the physics student learns, like how to recognize relevant and irrelevant informations, what information is needed to solve, or how to develop a model, or something like that. Now, I think that in a sense, these are things that every citizen should learn. Maybe in a more restricted way, but in some sense, people need to learn how to recognize relevant and irrelevant information. For example, to choose between two candidates to vote. So, in some sense, these are things that people should learn from high school, for example. And I was thinking if the lack of ability that the students have when they enter into college is actually revealing some of the deficiency in high school or before the undergrad education.
Okay, I completely agree with you. In fact, many times I've said that when I look at the graduate students in my lab and I look at what is really holding them back, and I say, this is something they should have learned when they were 5 years old in kindergarten. They should have learned that when you start this project, you hit a roadblock, you work on that roadblock, and hit another roadblock, you go work on that, and then You get this one done, you go back to that one, and then you go back to the main thing. You don't get distracted. You should learn that in kindergarten, right? But you look at our high school system and how a student gets into a good university, and what do? They're on a high-stakes test, and they get an answer, and something is going off saying, maybe this isn't right. I should really check over this answer. Is that what they should do? Heck no, it's a time-limited test. And if they spend time checking over some answer, they do badly on the test, okay? So now they're doing their homework. It's late at night. And they have to decide between calling up some friends and trying to get them to vote so that they're going to be the president of the debate society and put that on their resume, or they have to do some more checking of their chemistry problems. What should they do? They want to get into Harvard. They want to get into probably University of St. Paul. They better get through this assignment, get it done, and not ask whether the answer is right. So I would argue in many cases high school is counterproductive. I remember a history course in which the final exam was going to be one of 5 multiple choice tests with 100 questions on it, and I had to memorize all the answers. Who was the Secretary of State in President Franklin Roosevelt's first administration? I mean, I think it was Henry Stimson, but I don't know. And what difference does it make? I don't have any understanding at all. Okay? But so I think many times our education, but I can't change what happens in high school. I can change what happens in a university, in my class, and I can change and I know how to teach university level students, and that's what I'm trying to do online.
Are there studies being conducted in the high school level as well as you are doing?
Yes, but high school, schools in general have so many different people. They have the teachers union that's trying to reward the old teachers and not select out the best teachers. They have the administration. They have the people who are the janitors who need jobs in these schools. They have the parents. They have the students who don't want to learn too much. And everybody's pulling in a different direction. And it's very, very hard to move the system in any systematic direction. So in a way, I'm going to have to give up on that, or at least it's not for me, okay? But I will say one other thing, and that is, another way you teach experts, okay? Let's say that I want to teach you to play chess or tennis, okay? Then if it's tennis, okay, so I'm going to get a coach, and the coach is going to say, you have to be able to serve here with the spin on the ball so it kicks out that way. And so I get a bucket of 50 balls and I practice just that. And every time I practice that, I can see if the ball hit in bounds and I see if it kicked out that way. And after a while, I get really good at that particular skill. And that process is called deliberate practice. Then when I get in the game and I see that my opponent's over that way a little bit, I just automatically hit that serve and my opponent can't get there. But I'm able to think at a higher level because I've automated this procedure. In physics, when did we ever give deliberate practice on recognizing whether energy is conserved in this problem or not? That's all you have to do is just tell me, is energy conserved and why or why not? That would be deliberate practice in physics. And that would be a good way to make people into experts. Because we could give them 25 or 30 problems like that in an hour or 2 hours. Whereas we can only give them 5 big complicated problems that involve energy, at the end of which they're not any good at recognizing whether energy is constant in a new problem or not. So we're trying this method of deliberate practice, and maybe in a year I can come by, or 2 I can come by and tell you that it works or that it doesn't work.
There's this problem, you say F equals MA, right? Then the students ask, well, how do you prove this? Okay. I say you can't, because you have to measure time, okay? How do you measure time? Well, with a pendulum. How do I know it's isochronous? I use Newton's law, right? So essentially I can't do it. So a law means you have some idea and then it's consistent with a lot of facts and so on, it's no contradiction, but you can't prove it exactly like that. So law, or even what a law means for a physicist is not quite clear.
Okay, well, I want to dismiss objections based on Gödel's theorem, if you know what I'm talking about. The Gödel's theorem says you cannot make a logically consistent set of mathematical assumptions and deductions, and he can show you how to give a general counterexample in case you think you can't. Okay, so you have to assume certain things like you have a standard of mass, you have a standard of length, you have a standard of time, and that's what Newton did, and he got attacked later for assuming that time, universal time, in and of itself, rolls continuously on by, or something like that. And then Einstein said, hey, look, Mr. Newton, I respect you a lot, but actually you can't even tell the difference between time and distance. Okay, so at some level, if you go slow enough, then that doesn't matter. Okay, but there's a lot of, we do discuss, but only at the end, what is the epistemology? What is the physics in F equals ma? And is it just a method of measuring force or of defining how to measure force? Because that's what the Newton, the unit of force, is the meter times the kilogram times a meter divided by second squared, okay? So it's just defined in terms of other units. Is that just a definition? No, why not? What is the physical content of that law? And so on and so forth. So we do discuss some of that, because that's important, although we don't put it on the test yet. But we should. If we want the students to learn that, and it is important, we have to put it on the test. But at the end of the day, we have to decide what we want our students to learn, what's most important for them, or to remember us by, or whatever, and tailor the course to do that, because we can't teach everything.
The Finnish system of education is usually taken as an example, right? Of course, there are several problems into making a system that works in a country of a few million people into a system, a working system in a country that has as many 200, 300 people. Yet there's one thing in their system that's really, really interesting. And I had a chance to work with something quite similar. That's the problem-driven learning. So instead of saying, let's teach you how acoustics works, I say, hey, why don't you build an acoustic room? Tell me what kind of materials you need.
Yep.
And so they can learn about sound absorption and reflection and everything else. I say I had this experience in a competition. It's called IYPT, International Physicist Tournament.
Mm-hmm.
And I have to say, that's the place where I learned the most.
Mm-hmm.
There were problems like
now.
drop a magnet into a pipe, into a metallic pipe, and study its motion.
Right.
So,
Look, okay, so first of all, with respect to the IPT or the Physics Olympiad or any one of those things, you have to already be an expert before you can profit from those experiences. But let's get back to the Finnish model, which is probably embodied mostly in the what's called project-based learning. Okay. I think there's a real place for project-based learning. I think building a robot or whatever, building a bridge out of straws or little sticks, those, you can learn a lot that way. I'm not and Eric Mazur has switched now from pushing concept learning to reforming the freshman course with project-based learning. He now has enough cachet, or respect in Harvard to change Harvard freshmen and to see, at least to get permission to do that experiment. I'm not sure that's the way I want to go. I really want to exploit online education, but I think there's a lot to project-based learning.
Yeah, I have to say I was very impressed by the way you seem to have been able to perform controlled experiments in the field of education, which, as I understand, is not a trivial thing to do whatsoever. Right. I was interested particularly in the case where you were following the students who had failed the previous autumn and were being retested the summer, whatever. You said that was very TA intensive. Was it more TA intensive than it would have been normally? Is it possible to eliminate? What is the effect of just having more attention being given to you rather than the method itself? I mean, we all know that if you go to the doctor and he spends 50 minutes with you, your chances of getting better are more than if he only spends 10 minutes with you. What extent is the personal attention a factor which needs to be discounted in one way?
Okay. I think that that we've always taught expertise by the apprentice system. I mean, you come in and you're an assistant and you sweep the floor, and then you're an apprentice and you agree to go a certain number of years, and then you get to be a journeyman, and then finally you present your master work and you get to be a master. And that's exactly what we do in graduate education. And I'll tell you the definition of a journeyman, and you will immediately recognize that it's a postdoc. A journeyman is someone who has finished his, or her, I suppose these days, apprenticeship, and is allowed to do minor projects by themselves, or to do major projects and supervise apprentices under the guidance of a master. Now, what does a postdoc do? Just that, right? And this business where someone who's an expert and knows what's important gets to talk to that person, watch what they do, show them what to do, watch what they do, give them feedback. That is really what students have to. Why should they come to MIT and learn from someone like myself, who is really in the top echelons of being a physicist, rather than at San Diego State, someone who's not so good? Probably, maybe for mechanics, it doesn't make that much difference if that person knows about education research. But at the higher levels, it does. Okay, so I think that what you come down to is that the students are paying their tuition to interact with us, not to watch us perform lectures. Okay. Now, I didn't answer the whole question. What else did I want to say? So I think what we have to do in order to keep the price of education under control is to figure out how we can emulate a lot of the interactions that happen between an expert and a student. Either automate them, as we did in Mastering Physics. Okay, in Mastering Physics, our big insight was to take all the wrong answers, like 1,000 wrong answers. And since they were analytic, we speak that language. And so we could go back to the teacher and say, to me if I wrote the problem, and say, okay, here's a list. 15% of the students gave this particular wrong answer. 12% gave that one, 11% gave that one, 10% gave that one, 10% gave that one, 9%, and so on. What do you want to say to the next person who gets that response? What would be the expert response to a student who gave that wrong answer? Okay, and so I type that in, and then half the time the students get a particular response to their wrong answer. And it's like an expert. So it emulates some of what experts really do, because you automate the expert response, okay? As far as the TAs are concerned, we use a lot of undergraduates, and so I beat on them and tell them never say yes, that kind of stuff. And maybe what we could do to really scale it up is to have some of the better students in the class go around and help the other students. When they're done, they're finished first, they should go around and help the other students. The trouble is we want to somehow ensure that they give the expert type of advice rather than just saying, oh, see, look, I have this equation, I have that equation, and then I divide by 2 here, and then I can eliminate that term, and then I can get the answer. That's not helpful. Okay, so, and I don't know how to do that. And at MIT, frankly, there's not a lot of incentive for me to do that, because I've been to places, one place to find out a good source of how you can use online to cut down the cost of education is the National Center for Academic Transformation, .org, which is not really a national center, but it's a good place. And I went there once and I gave a keynote talk, and I was blown away because these people would get up and say, well, in introductory mechanics, our cost per student semester is $343, and after we adopted your program, it was only $270. And I went to my department head in physics, and I said, 3 years ago, we switched from classrooms to this TEAL, this more interactive format. Do we know how much more expensive it is? Because it obviously involves more people. And his response was, no, I don't know how much it cost before, I don't know how much it costs now. We need those resources to do it well, and we're going to find the resources. Well, that's a great attitude if you're MIT, right, and you have a big endowment. But it's not the way we're going to teach everybody. We have to be more like the NCAT. And we have to figure out how to teach like an expert, not using experts, because experts are expensive.
Okay, so I think we are ready for the coffee, and I want to thank you, David, for coming
Okay.
from Boston to here, and I hope you'll return
Okay.
in the future and tell us more about.
Okay, good.
So let's give a good thanks to David.